Hi everyone, in this video we're going to be going over the derivatives of the inverse trig functions. I want to begin with example 7 by deriving the formula for the arctangent of x. The derivation here will not be anything too crazy, but it will be requiring us to use implicit differentiation. I'm going to go ahead and begin here by defining y as the arctangent of x. So if we have here y as the arctangent of x, then I'm going to go ahead and take the tangent of both sides to get rid of the arctan. So now that we've gotten rid of the arctan, we have here that tangent of y is equals to x. And here is where the implicit differentiation comes from. I'm going to go ahead and take the derivative of both sides with respect to x, which will give us the following. The derivative of the tangent, if you recall, is the secant squared. So we have secant squared of y, but this being an implicit differentiation, where we don't know what y is, but we assume that it is a function of x, I'm going to go ahead and now multiply by dy dx. Now what about the right hand side? Well, what is the derivative of x with respect to x? That is a nice 1. Okay, well, now it's a matter of getting the dy dx by itself, which we can get by dividing by the secant squared, which I'm going to do in the next step. So now we have dy dx is equals to 1 over secant squared of y. However, this doesn't get us anything close to figuring out what is the derivative of the arctangent because, well, now we have the function y here. And it's a little bit of a problem. However, I'm going to go ahead and make use of the Pythagorean identity to see if I can maybe find out a relationship between a secant squared of y and a tangent squared of y. Now, we get to see here is like, okay, well, if I have sine squared of y plus cosine squared of y is equals to 1, then if we divide everything by the cosine squared, we will be obtaining a new form or a different form of the Pythagorean identity, which gives us sine squared over cosine squared, which is tangent squared of y, plus the cosine squared over cosine squared, well, that's 1, is equals to 1 over cosine squared of y, which is the same thing as secant squared of y. Oh, well, look at that. We know that secant squared of y is the same thing as tangent squared of y plus 1, which I will rewrite now. So now we have dy dx is equals to 1 over tangent squared of y plus 1. Now I'm just going to go ahead and extend the fraction here. There we go. Alrighty, now you might be thinking, well, what good does that do to us? Because, well, we're still having a y here, which is true. Nonetheless, recall the way that we defined the tangent of y. We had here that the tangent of y was equals to x. So now I'm going to go ahead and make one more substitution and say here that this tangent squared of y is really the same thing as x squared. And that now gives us our desired derivative. We're going to have dy dx here, being the derivative of the arctangent, is equals to 1 over x squared plus 1. And there we go. We now have the derivative of the arctan. Now, for the next problem, we want to derive the formula for the arcsine, but this is something that I'll let you guys try on your own, or most likely in a discussion board. In the meantime, though, I'm just going to go ahead and give you the formulas here. So these are the derivatives for the inverse trigonometric functions. Now I listed here memorize 1, 2, 3, but really, what you should memorize here is formula 1, formula 3, and formula 5. The reason I'm asking you guys to memorize these formulas is because if you notice, all the formulas, or some of the formulas, look very much the same, with the difference being that some of them are positive, some of them are negative. If you take a look at the derivative for the arcsine is 1 over the square root of 1 minus u squared times du dx, but the derivative of the arccosine is negative 1 over the square root of 1 minus u squared times du dx. It's the same thing, it's just that the sign is different. When you take a look then at the arctan, well, the arctan here is 1 over 1 plus u squared times du dx, and if you take a look at the arccotangent, it's a negative 1 over 1 plus u squared times du dx. Again, same thing, except that one of them is negative. And lastly, for the arcsecant, the one that you should also memorize, it's 1 over the absolute value of u times the square root of u squared minus 1 times u dx. And the arccosecant, it's the same thing, but it is negative. So if you know the derivative for the arcsine, the arctangent, and the arcsecant, then you pretty much have the derivatives for the arccosine, arccosecant, and arcotangent. You just need to multiply them by a negative. Alright, so with these formulas here, readily available, let's go ahead and take the derivative for a couple of problems here. And I'm going to go ahead and begin with the first one here, asking us to find out the derivative of 4 times the arctangent of 2t. Okay, so if I want to go ahead and find the derivative, let's see what we're going to get. So we have a 4 that's a constant, so we're going to have here 4 times the derivative of the arctangent of 2t. Now this 2t is going to be representing our u. So the derivative of u, or u prime, is going to be equals to a 2. Alright, now which one was the derivative of the arctangent? Well, as we derived it, we know it was going to be 1 over, well, switching the x's with the u's, is going to be 1 plus u squared, our u being a 2t, so now we're going to have a 4t squared times the derivative of u, which is a 2, giving us our final answer of 8 divided by 1 plus 4t squared. Okay, so now let's take a look at another one here. So for the next problem, we have p of x is equals to 16 times the arcsine of x over 4. Alrighty, now this one here, I'm going to begin by, again, identifying our u. So our u here is x over 4, and the derivative of u prime, is going to be 1/4. Okay, so what will be then the derivative? Well, we're going to have here p prime of x is going to be equals to, now remember that the derivative for the arcsine, which I'll write here above, is equals to 1 over the square root of 1 minus u squared times du dx. Okay, so we identified our u already. We got the u prime, or the du dx. So now, putting everything together into the formula, we're going to have here a 16 that's a constant times 1 over the square root of 1 minus u squared, so 1 over x squared over 16 times du dx being 1/4. Alright, now I'm going to go ahead and simplify this one. 1/4 times 16 is going to give us a 4. So we're going to have here a 4 over, now we have a 1 minus an x squared over 16. I want to put everything in a single fraction, which I will rewrite as the square root of 16 minus x squared all over 16, which we could simplify a little bit more here by taking the square root of the 16 in the denominator. So we're going to have here 4 over 1 over 4 times the square root of 16 minus x squared, which will now give us here, so 4 divided by 1/4 is going to be equals to 16 over the square root of 16 minus x squared. And there we go. This gives us now the derivative for 16 times the arcsine of x over 4. Alright, so now let's take a look at one more problem here, which looks kind of tricky, certainly looks scarier. So for problem C, we have f of x is equals to 2x times the arccosine of x minus 2 times the square root of 1 minus x squared. Alright, so I like this problem a little bit more, seems more engaging. Alright, so a couple of things to note here. For the first term, we are multiplying a 2x times the arccosine of x, which means that we need a product rule. Alright, so I'm going to go ahead and use a product rule, which says that, hey, anytime that you're multiplying two functions, f times g, where I'm going to call f the 2x and g the arccosine of x, then that derivative will be f prime. So we're going to have here the derivative of 2x, it's a 2, times g, so times the arccosine of x, plus, now it's f, so 2x, times the derivative of g, which in this case I'll write in green. So what is the derivative for the arccosine? Remember, this one is the same thing as the arcsine, it's just that it's negative, so I'll put here as a negative 1 divided by the square root of 1 minus a u squared. In this case, there's no need for us to use a u, it's just x. So we're going to have 1 minus x squared. Okay, so this takes care of the product rule. Now let's take a look at the second term, where we have minus 2 times the square root of 1 minus x squared. Now remember, using radicals with calculus, there's no rule for it. We need to rewrite it as rational exponents, so the square root is the same thing as the 1/2 power. And there we go. Now it looks nicer, I would say. we can get to see that, oh yeah, it is a chain rule problem. So we're going to have here a minus 2 times the derivative of 1 minus x squared to the 1/2, which will give us times 1/2 times 1 minus x squared to the negative 1/2 times the derivative of the inside. Now the derivative of 1 minus x squared is going to be a negative 2x. Okay, now I'm going to go ahead and keep on simplifying the problem, but first I'm going to make sure that we are saying that we are taking the derivative here. So we're going to have f prime is then going to be equals to 2 times the arc cosine of x minus 2x all over the square root of 1 minus x squared. Now what simplifies on the last term? Well, I get to cancel this 2's. Now I also see a negative times a negative, so we're going to get a positive. Now what else do we have? Well, we have a 2 on the top, and on the bottom we have a square root of 1 minus x squared. Oh, well, look at that. We have a negative 2x over the square root of 1 minus x squared plus a 2 over the square root of 1 minus x squared. We can go ahead and cancel them, which gives us a final answer of 2 arc cosine of x. And there we go. This was here our derivative. Alright, so now let's take a look at another classical example involving derivatives, where we're being asked to consider a function, and we want to figure out what is the slope at that point, and what is the equation for the line, or the equation for the tangent line at that point. So for example 10 here, we're being asked to consider the function x squared plus x times the arctangent of y equals to y minus 1 at the point negative pi over 4, 1. So given this information, we want to figure out what is the slope of the line tangent to the function at that point. Alrighty, now, very typical example, but there was one caveat here. In fact, you might have noticed that this equation here has both an x and a y. Okay, well, no worries. We've already seen an example that had an x and a y before when we derived the derivative for the arctangent function. So, you guessed it, we are going to be using implicit differentiation. Alright, so let's go ahead and copy our problem here so we can go ahead and take the derivative of everything with respect to x. Okay, so here's an equation, and now I'm going to go ahead and take the derivative of everything with respect to x. Okay, so let's see, what is the derivative of x squared with respect to x? What's nice, it's just 2x plus, now we got to be careful here because we have an x times the arctangent of y, which means that we need the product rule. Alright, so according to the product rule, we're going to get here the derivative of x is 1 times the second function, the arctangent of 1, plus, now it's x times the derivative of the second function, and the derivative of the arctangent of y is going to be 1 over 1 plus y squared. But remember, this one here is a function of y, and we are assuming that y is a function of x, so we need to go ahead and multiply times the derivative of y with respect to x. Okay, now we have that this is equals to the derivative of y with respect to x minus the derivative of 1, which is a nice big 0. Alrighty, so here we have our derivative. Now we need to go ahead and figure out, okay, well, what is the slope at the point negative pi over 4 and 1? Well, there's multiple ways of doing this one here. We can go ahead and isolate the dy dx and then plug in our values for x and y given here. But another approach, which I like to do, is plug in the values now and then isolate the dy dx. So I'm going to go ahead and plug in the values for x and y to see what we get. So we're going to have here a 2 times a negative pi over 4 plus a 1 times the arctangent of 1 plus x times 1 over 1 plus y squared, so 1 plus 1 squared times dy dx, and this is equals to dy dx. Alright, so simplifying a little bit here, we're going to have a negative pi over 2 plus 1 times, alright, so what is the arctangent of 1? In other words, what is the angle whose tangent is 1? Well, the only angle that fits this description is a pi over 4 plus, well, technically I suppose now it's not a negative pi over 4 times 1 over 1 plus 1. It's going to be a negative pi over 4 times a 1/2 dy dx, and this is equals to dy dx here. Okay, so simplifying things a little bit more, negative pi over 2 plus pi over 4, that's going to give us a negative pi over 4 minus, so now it's a pi over 4 times 1/2, so that's a pi over 8 dy dx equals to dy dx. Okay, so we're almost done. Continuing it here, I'm going to go ahead and now isolate the dy dx. So I'm going to have a negative pi over 4 equals to a dy dx plus a pi over 8 dy dx. Now factoring out a dy dx on the right hand side, we are left with dy dx times 1 plus pi over 8. And this one here is equals to a negative pi over 4, which now gives us dy dx equals to a negative pi over 4 divided by 1 plus pi over 8. Now, I don't like having complex fractions, so I'm going to go ahead and multiply by the LCD of everything. So that LCD of every single fraction, that's an 8. So I'm going to go ahead and multiply everything by an 8, which will give us our final result of dy dx is equals to a negative 2 pi divided by 8 plus pi. And there we go. Now we have the slope at the point negative pi over 4, comma 1. All right, excellent review of implicit differentiation. Alrighty, now for part B, we're being asked to find out the equation for the line tangent to the function at the given point. Now remember, anytime that you're trying to get the equation for a line, doesn't have to be the tangent, you need a point, which we do have. It's negative pi over 4, comma 1, and we need a slope, which we just found. Since we're looking for the slope of the tangent line here, we use a derivative, and we got a negative 2 pi over 8 plus pi. All right, now we can go ahead and use the point slope formula, where we're going to have y minus y1, or let's go ahead and use function notation, which we're going to have f of x minus f of x1 is equals to the slope, which is the derivative evaluated at x1 times x minus x1. Okay, so this is going to give us now f of x minus f of x1, or the y value, which was a 1, and this one here is equals to the slope, which we had negative 2 pi over 8 plus pi times x minus x1. So x1, if I'm not mistaken, was the negative pi over 4, so negative and negative turn into a positive. And there we go. Here we have the equation for the line. There is no need to isolate the f of x. This equation here is perfectly fine. It is the point slope form. Okay, so this was the final example on derivatives of the inverse trigonometric functions. In the next video, we're going to be going over some of the integrals for the inverse trig functions. See you there.